Well, thanks so much for the kind introduction. And let me just say, it's a real pleasure to be here today to tell you all about ways in which we can use our universe basically as a giant particle physics experiment to try to learn what are the building blocks of our universe and how do those building blocks interact with one another. Now, when you see something like dark forces here in the title, you might get nervous. This might be something that comes into your mind. But no offense to Darth Vader, but that's not, we're not talking about science fiction here today. So in spite of the fact that, talking about dark forces might sound a little bit out there, really this is something where, we're living in an epoch where we have a lot of astrophysical data coming in. And so here are just a couple of examples. You may recognize these all as examples, which can actually inform our understanding of how building blocks of our universe behave and whether or not there could be additional forces and particles beyond what we already know about. So this is really a data-driven question. This is a scientific question. We're using the scientific method, okay? And so because this is something where we want to say statements with precision, let me be precise about my terms here. So going back to the title, so searching for the invisible. So Merriam-Webster would define something that's invisible as something that's incapable by nature of being seen. I want to be a little bit more specific. So for the purposes of this talk, invisible is going to mean something that is fundamentally transparent and does not interact very much with light, right? So this comment about being seen kind of implies light because we're used to seeing with our eyes, but I'm really wanting to make that point explicit. And in this talk, I'm going to show you that just because something fundamentally doesn't interact very much with light doesn't mean that we can't discover it. I think that is probably very apparent to many of you in the room now that we are living in the era of multi-messenger astronomy. And so the other point I'm going to convey to you is that dark forces can have observable consequences on what we see, even if we can never directly feel or interact with those forces. So that's the plan for today. And before I tell you about looking for dark forces, I want to quickly review what is known, so what we know so far about the building blocks of our universe. So here's a diagram of how I like to think about the standard model of particle physics. And I've organized it here by the different kinds of particles and what forces they feel. So this gobstopper over here is kind of like a Venn diagram of particles and forces. And as you can see already from this picture, right, this is actually kind of a complicated theory. We've got all these various particles in here, all these forces. Most of what we see and most of the mass of the universe that's in these kinds of particles is really in protons and neutrons, but there seem to be all these other kinds of particles as well. And beyond just the fact that there are many particles and many forces, there's a lot of hidden structure that this diagram does not actually reveal. So, not to get too jargony and particle physicsy, but right, some of these forces are have non-abelian gauge groups. We've got the Higgs mechanism. We've got the hierarchy problem. These neutrinos over here have some unknown mass, which is not explained in the standard model. We've also got CP violation over here in the weak sector, but not in the strong sector. Main point really is that this theory is really rather complicated. And so given all of the structure that exists here, we know that there are places where we see that there's evidence of some new kinds of particles and fields. And so hopefully it's not too much of a stretch, it's not too inconceivable to think that because of all of this rich structure over here, this evidence that we have for new particles could be actually equally as rich as what's going on over here. There could be additional auxiliary particles and forces that come along for the ride with the discovery of new kinds of matter. Now, if this is the case, we might get lucky, okay? Nature might be kind to us, and we might be in a situation where if there are new forces, for example, those new forces could talk directly to particles in the standard model. And so here are a few examples from my work where we can actually make use of these portals, these new forces, to try to learn about what is happening internally inside of this new sector, okay? And so here's some examples of how this can work. You might think that this is where the story ends, that if such a portal doesn't exist, then we're kind of lost. So you can take a pessimistic kind of view and say, well, what if this new force is totally decoupled? It's not directly talking to anything. But it turns out, even in that case, and here are some examples again from my research program, even in that case, you can still learn about what's happening inside of this sector because of the miraculous fact that gravity is universal. Okay, so anything that has energy or mass is going to gravitate. And so because at a very minimum, we have this gravity portal to this visible matter, we can try to use that to learn about what's happening here, right? So this is kind of akin to, we actually used gravity in the first place to say that we think that there's a new particle in here, and so we're going to continue to use gravity to learn about, any auxiliary particles and fields. So the plans, just to be a little bit more specific for the rest of the talk, is to show some examples of astrophysical systems where we see gravitationally evidence for new kinds of particles. These systems that I'm going to talk about in my talk span 9 orders of magnitude in length and 17 orders of magnitude in time. So that's providing a huge lever arm, a huge diversity of different systems, different length scales and time scales, where we can test different kinds of theories. And this is going to be a program I'm going to illustrate in my talk today, where we're constraining properties of particles based on how systems look to us. So this is a very empirically driven outlook that I have. And so, in other words, I'm really playing with the universe. I'm trying to tweak the theory of the universe and then see what it looks like, and I'm trying to do that to look for new forces. Personally, I have a lot of fun doing that, and I can see this being really fruitful and other people having fun doing this. So let me first start fairly locally by talking about things happening in our galaxy. Okay, so by the way, this is not a picture of our galaxy, right? Of course, this is Andromeda. I'm going to be using it as a visual proxy to talk about what's happening in our Milky Way, because of course we can't take a picture like this of our Milky Way since we're embedded inside of it. But if we look at galaxies like our galaxy, right, like Andromeda or like the Milky Way, we see evidence for dark matter. And this is pretty generic if you look at galaxies. When you look, of course, at the rotation curves, you go to larger and larger galactocentric radii, and you look at the speed at which things are rotating. What you'd expect from the visible matter over here is that the speed should go down, right? The gravitational potential is less deep, further away from this visible matter, and so the speed should accordingly go down. But that's not what we see. So when we look at various tracers of the speed of rotation, it seems like things are actually leveling off or even increasing slightly at larger and larger radii. And you can't account for that with just the visible matter that you see here. So another way to put that is that in the absence of additional matter to bind things down, things at the outskirts of galaxies would just fly apart, okay? So you need some additional matter to bind things down. And by studying dynamically different kinds of galaxies, the emerging picture is that in many galaxies, including in galaxies like our Milky Way, we think that there's a galaxy that's embedded in this really large, puffy dark matter halo. And this picture is roughly actually to scale. And so naturally, that's calling out for some explanation. Why is the scale here so different? And so the kind of glib answer is that visible matter can cool down, right? So the fact that visible matter, right, baryons are able to cool down, they're able to lose energy, whether it's ionized, so whether you can emit by Bremsstrahlung or synchrotron radiation, or whether it's neutral atoms, and then you have atomic cooling lines whereby you can cool down. Regardless of the mechanism, the fact that it can cool down means that you end up having a disk, right? Because you can lose energy, but you can't radiate away angular momentum. And so this is the configuration that satisfies that. And so that's why you end up with this disk here. And the standard story that explains why the disk looks so different from the big puffy dark matter halo, the standard story is that dark matter does not cool down so efficiently. And so that's why you have this kind of morphology. The dark matter is just inert, it's just kind of passing through, and it's only interacting gravitationally, so it's never able to lose energy and shed energy. Well, let's push on that assumption, right? Because that's kind of an assumption at this level, and let's ask the question and really try to be quantitative and say, well, what if some of the dark matter could cool down, right? So we obviously see this big puffy dark matter halo, so most of the dark matter has to be in that halo, but what if just a little bit of the dark matter could cool down? And just to make a direct analogy to the standard model, to what's going on, it could be the situation where you have new kinds of dark forces where you're emitting a dark version of a photon, right? So you have some light mediator that you're radiating away, and you're creating a situation where the dark matter can cool down and potentially also form something like a disk. So we want to quantify to what extent this is possible. And to quantify that, we're going to be looking for extra contributions locally to the gravitational potential in the disk. And this is interesting also from a particle physics perspective, because as I just mentioned, this has implications for new forces in particles, right? So it would tell you that there has to be multiple components of dark matter. It's not just one thing necessarily, and it would tell you that there's new forces, so that's pretty cool. It also has relevancy for techniques that we use to try to look for dark matter in the lab. So if we live in a dark matter disk, you actually have to really consider that carefully when you're trying to do a direct detection experiment where you're waiting for dark matter to come in from the galaxy and hit your detector. So that's going to have implications for that as well. Okay, so we want to quantify, we want to look for gravitational, we want to look for contributions to the gravitational potential. The way that I did that is by using Gaia. So many of you in this room are familiar with Gaia, but just to quickly recap what Gaia is doing is it's getting pretty accurate positions of stars. It's looking roughly at 1% of the stars in the Milky Way, and it's basically monitoring the positions over time with this level of accuracy. I'm a particle physicist, so this number didn't mean anything to me. I had to actually go on Wolfram Alpha and start plugging in, okay, what is this in radians, and then what are the kind of length scales, what are the ratios? It turns out, so the numbers that I settled on are that if you had the ability to find things with Gaia's resolution, with that kind of localizing capability, you could find a quarter on the surface of the moon from the Earth, and I think that's pretty amazing. So just thought I would share that with you all. And so with that kind of information, if you're monitoring the stars over time, you get information about their proper motion, so how fast are they going projected onto the celestial sphere. You get depth perception from parallaxes, and you also have the spectrometer for line of sight velocities. And so with that information, you can try to reconstruct the six-dimensional phase space to the extent possible. Now, we were doing an analysis looking for, as I mentioned, a dark matter disk. So again, using Andromeda as my visual proxy. If I think about this region as being centered on the location of the sun, we were really looking in a very small region of interest, using Gaia to look for contributions to the gravitational potential. Now, right, if you just think about where is the difference going to be the most dramatic, or how are we going to be able to see this in the most effective way, right? The scale radius of this disk, right, is on the order of kiloparsecs, so it's not changing very much in the solar neighborhood. Really, the relevant direction is what's going on in the z direction, right? The aspect ratio of this disk is really rather extreme. So if we want to look for a dark matter disk, the most obvious place to look is, looking for changes in the z direction to the gravitational potential. That's going to be where the changes are going to be the steepest. And what you can actually show is that in the region where you're very, very close to the disk, that z motion really dominates what's going on. Right, the potential is so steep in the z direction that the motion in the z direction decouples from what's happening in the radial direction and in the phi direction. So that's really the direction we're going to be honing in on for this analysis. And so let me just quickly tell you what we're going to be doing. What's the goal here? So let's say we have some tracer stars. So these are our tracer stars. These are just stars that are, not contributing a whole lot to the gravitational potential, and so we can really think about them as being darts that we throw. And we try to see from the trajectory, what's going on, what is the underlying gravitational potential. So here are my tracer stars, and what I want to do is I want to predict where they go. What is their distribution as a function of height, z, above the galactic plane. So I start at the origin at z equals 0, the midplane, and then I initialize my darts. I throw them with some distribution of speeds, which I can measure in Gaia. So here is the measurement from Gaia. And then I see how far they can climb out of the gravitational potential. Now, when they climb out of the gravitational potential, you have to pay this 2 phi price, which comes from the virial theorem. And so what we're doing here is we're saying, okay, we can measure this distribution of speeds. We can also measure this, and I want to try to connect them to one another self-consistently with this connection, which is this gravitational potential. So here we have some information about the gravitational potential from visible matter, say like the gas and the stars in the disk. And then optionally on top of that, we're going to put a dark matter disk and see to what extent these two observable quantities here are consistent with one another. So just to see how this looks, if you just plug in the known baryonic components and you just take at face value the measurement, you don't vary them or marginalize or do anything, just this is a 0 parameter fit. Okay? And you say, how does this look? Turns out it looks something like this. So it turns out that the prediction from the distribution of speeds and the potential of the known baryons, that prediction, which is the solid line, matches extremely well to the data. Okay, and when I saw this, I got quite excited because this just seemed like an amazing agreement. And then when you change the gravitational potential, when you add a dark matter disk, and again keeping all of the parameters fixed, it looks like this. Okay, so obviously these things are not consistent with one another, Now, I'm fixing all of my inputs from the baryonic contributions to the potential. Of course, those quantities are kind of uncertain at between 10 to 30% level, depending on what component of the baryons I'm talking about. And so, of course, if I change some of those densities a little bit, I can mitigate some of this difference here. And so some of this difference can be absorbed into just not having a perfect reconstruction of my baryonic mass model. But that's only allowed to a certain extent. So to actually quantify to what extent this difference can be mitigated, we basically were looking at trying to understand all the various nuisance parameters that existed in our analysis. And so we were profiling over likelihoods to set a limit on a dark matter disk with scale height h and a surface density sigma. These were our model parameters. And then we were really doing a full exploration of parameter space of all the different parameters entering into our modeling. All in all, there were 90 nuisance parameters, so we needed to make use of some computing resources to do this analysis. And really, we were trying to be as conservative as possible in everything we were doing, really trying to make sure we're not overstating any claims about the possible existence or lack thereof of a dark matter disk. And the upshot, when we did our analysis, is that less than 1% of dark matter can be in a baryon-like disk. So this is already something where we're able to make percent level statements. So if dark matter has some way it can dissipate energy efficiently, it had better be that less than 1% of dark matter is doing that in a way where it ends up looking like our baryonic disk. Okay, so so that's the upshot from this analysis. Now I want to go slightly further away and talk about subhalos and the dwarf galaxies that live.
Sorry, Katelin, can I ask about the scale height of this dark disk?
Yeah.
Are you making an assumption, or are you making a statement about the scale height?
Yeah, so I don't have a slide on that, but basically we were assuming that it was of a comparable thickness to the baryonic disk. And if you, maybe I can just draw it over here really quickly. Yeah, we had two parameters in our search. One was the scale height, and one was, one was the surface density, and one was the scale height. And yeah, so we set some limit like this. So anything like above here is ruled out. Yes.
Since we're on the disk, can I just ask this question before you go on? So the other things that have come out of Gaia have shown that the disk is not in equilibrium, which is fundamental to your assumption here. So
yes.
Can you still hide the disk by saying, well, actually the models, this isn't really the right model that we're using?
Yeah, I'm so glad you asked me that question. So I agree. I do not think that the galaxy is in equilibrium. However, I think if there's any chance anywhere in the galaxy for things to be well equilibrated, it's very, very close to the midplane of the disk, because the density of stars and the density and the potential is so much steeper there. So the time scale for things to settle down is much, much shorter than it is, say, a kiloparsec off of the disk, where a lot of out of equilibrium behavior is most readily apparent. So we did a bunch of checks in our analysis to check for any signs that out of equilibrium behavior was affecting our results. And so we were checking for Gaussianity of the velocity statistics. We were checking for symmetry of both the velocities and of the densities. So that looked actually really rather symmetric, and it wouldn't if there were out of equilibrium behavior affecting our analysis. I also showed 3 different populations of tracer stars, which we actually separated our analysis by looking at different tracer stars with different dynamical temperatures. Right? So what you would expect is that in the presence of out of equilibrium behavior, these different tracer stars would settle down at a different rate because they have a different dynamical temperature. People have shown in simulations that if you try to use different tracer stars to measure, say, the density of dark matter, you'll get the wrong answer, or you'll get discrepant answers between different tracer stars in the presence of out of equilibrium behavior. But we did not see that in our analysis. And really, we were making also a bunch of estimates. I don't want to go too far into the details, but we were making also a bunch of estimates and including that into our error budget to try to account for out of equilibrium behavior. So yeah, really trying to do a lot of consistency checks. And at some point, it seems like in our analysis, it quacks like a duck. So that's the extent to which I can make any comment about that. But I would be happy to chat more if you're interested. Okay, thanks.
Sorry, one additional question following on that. Why do the different tracer populations have different vertical scale heights?
Good. I think that's actually, my understanding is that that's a couple of different factors coming into play. One of them is that these G stars are older. So when they were born, they were inheriting the kinematical properties of the gas out of which they were born. And at that time, the gas was just a little bit thicker. It hadn't cooled down to the level at the present day. So it's just a little bit thicker. So that's one reason. Another reason, and I learned this from talking to some simulators, is that it seems like some of these stars were not necessarily born at the solar radius, in the solar galactocentric radius. So some of them have migrated from other radii, and that also tends to puff things up. Yeah.
Thanks.
But I think that's something still people are still trying to get a better handle on. That's my understanding anyway. Okay, so now I want to move slightly further away from home and talk about subhalos and the dwarf galaxies that live inside of them. Now, these objects can be very, very dark matter dominated. So here is, for example, a picture of Eridanus 2, where approximately 99.7% of the mass of this object is in dark matter. And the standard story is that dark matter is pretty inert, it's pretty boring, and it's not doing very much. Now, the reason why we think that is because when we look at merging clusters of galaxies, say things like the Bullet cluster, of course this is one example out of now dozens, but when we look at these kinds of merging clusters, what we see is that there's a separation between where most of the mass is, inferred with gravitational lensing, as opposed to where most of the ordinary matter is, right? Because these clusters are merging very, very fast, right? The gas is getting very, very hot, and there's viscous drag here, which is slowing down the gas. So, right, this blob of gas used to be sitting inside of this distribution, but it got slowed down. There was some momentum exchange between this blob of gas and this blob of gas, which is why they both slowed down relative to the dark matter, which has just sailed right on through collisionlessly, more or less. And so because of these two regions not being co-located, not sitting right on top of one another, it seems like the dark matter is not scattering very much, and so it can't be feeling the kind of drag that the ordinary matter is feeling. But of course, you know, it's possible, right? So this is one type of environment, right? This is an environment where things are merging at around 1,000 kilometers per second. But of course, Ernest Rutherford taught us that scattering can have significant velocity dependences. So if you talk about scattering things off of atomic nuclei, Rutherford noticed experimentally that there's this low velocity enhancement, like v to the -4. And it turns out that this is, this scaling behavior is because photons, which are the thing mediating the scattering, are exactly massless. And so something analogous could be happening with dark matter scattering, where if there's some mediator that's mediating the scattering, if it's very low in mass, it could have some funky low velocity behavior. V to the -4 is what happens if it's exactly massless, but if you give this thing maybe a small mass, you can have resonances, you can get all sorts of non-trivial velocity behavior. And so, you know, I'm going to, again, push on the standard assumptions and ask on the flip side, which is what if dark matter could scatter quite a lot at lower velocities? And these kinds of galaxies would be a great place to test that because, again, they're so dark matter dominated, so it's a great laboratory to look for dark matter physics, and at the same time, the velocity here is several orders of magnitude smaller than what it was in these merging clusters, right? So if there's anything funny going on here at low velocities, this is a great place to test it. So people have studied this in simulation. So here is an example where people asked, well, what if dark matter could scatter with itself in this kind of velocity-dependent way? And so here on the left, I'm showing a simulation of collisionless dark matter, and on the right, I'm showing a simulation with self-interacting dark matter where it has this velocity dependence. And you know, if you quantitatively look at these two pictures, they look different, but if you just look with your eyes, if you just look qualitatively, it's pretty hard to see a big difference between these two pictures. And so, you know, myself and a couple of other people were wondering, well, can you actually qualitatively change what these kinds of galaxies actually look like? One way that you could do that is by looking at inelastic scattering, which actually nobody had really considered too much in the literature. There were a few really important papers, but it hadn't really been tested in simulation. And one thing that was prohibiting simulations was just a lack of an analytical good understanding of what was going on. So I worked this out with Tracy Slatcher, and we were basically looking at what would happen if you could have multiple dark matter states. So here I have Chi2, this is the excited state, could scatter into the ground state. And in doing so, if there's inelastic scattering, this could be exothermic, and you could be releasing a whole bunch of energy. These final state particles could get heated up and could get a pretty big kick. Alternatively, you could have endothermic scattering, where you have particles in the ground state that have to convert some of their kinetic energy into potential energy or into mass to get into the excited state. And again, if you have this low mass mediator here, again, you're naturally going to end up with velocity-dependent scattering. And so that's something where, again, dwarf galaxies would be a great place to try to test this and see if it's going to look qualitatively different. So we studied what would happen in this kind of situation. And for example, if you do want to look at the velocity behavior, it looks something like this, where if you look at the elastic scattering channels, so you see, these two are actually looking at ground to ground and excited to excited, and here I have ground and excited scattering off of one another. You can have an enhanced behavior for that, but also for the exothermic case, you can have a huge enhancement at lower velocities for exothermic scattering. Now, for this choice of parameters over here, endothermic scattering is not that important because basically, unless you're at very, very high velocities, the dark matter particles just moving around in, the ambient, let's say over here it's a cluster. It's very few of these dark matter particles that are going to actually have sufficient energy to upscatter and to actually be able to convert their kinetic energy into mass. So that tends to be less important in the toy model that we looked at. But really, exothermic scattering is quite important. And so when you simulate what this kind of dark matter does, so we worked with Mark Vogelsberger and Jesus Zavala to see how this would behave. It looks like this. Okay, so this is a pretty different situation where, even just by eye, you can see qualitatively that if you add inelastic self-interactions, it looks like everything has gotten really puffed out, everything has gotten really fuzzy. And the reason for that is actually because this exothermic scattering channel is so important. If you actually want to quantify that, you can look at how much energy particles have. What is the PDF? What is the spread of energy that these particles have? So if you look at CDM, right, so there's some peaked distribution. If you add elastic scattering, that peak moves a little bit to the right. So on average, particles are a little bit more energetic. But if you have inelastic scattering, so you have that same peak, but then you have a huge spike over here, where these are basically particles that got kicked in the final state because there was this downscattering. And these particles, basically have a lot of energy that's bigger than the binding energy of the halo that they're in. And so you end up with a substantial fraction of dark matter particles in the end of the simulation that are gravitationally not bound. And so that's kind of accounting for why things look so puffed out. If you also just try to quantify this by looking at the profile of these subhalos, right? So we know that in CDM, we get this cusp in the center, and we know that elastic scattering can core the profile. And inelastic scattering, it turns out, does even a more efficient job, because those particles that got kicked out of the halo, right, had they still been there, they would have made the gravitational potential deeper, and that's going to have implications for the other dark matter particles that don't necessarily scatter, right? So their orbits are going to be more tightly bound, but when you kick those particles out, the potential gets shallower, and so the particles that don't scatter are less tightly bound, and so you end up with this bigger core. So the upshot of what we've done so far is that inelastic scattering could, in principle, completely change how dwarf galaxies look. This is something we want to keep exploring, so running more simulations, understanding how baryons affect this picture, and then maybe even engaging with observers to understand to what extent is this actually even allowed. The fact that dwarf galaxies look like what they look like, can we say anything interesting about inelastic dark matter? I want to now move much further away from home and talk about clustering on cosmological scales and what it can tell us about dark matter. So here, the standard story is that dark matter is cold and does not interact very much with the primordial plasma. So this is a two-part statement, so let me break it down first by focusing on the statement that dark matter is cold. We know that because when we look at large-scale structure, right, things look pretty clumpy, and hot dark matter does not cluster as much. All right, so this is actually the way, this is the reason why we know that neutrinos are not dark matter. So in the early days of thinking about dark matter, by my own definition that I said in the beginning of my talk, by definition, these particles are dark, right? So these are actually some fraction of the dark matter because they have some unknown mass. And so people thought maybe these could be all of the dark matter. It turns out that these neutrinos are born in the Big Bang, so they have some hot temperature, and so they can't cluster as well. For example, if you look in simulation, here's a simulation with neutrinos as 20% of the dark matter, and you can see that over here, everything looks really fuzzed out relative to what's going on over here, right? So here, if you think about like power spectra, right? Here, like power spectra are kind of like variances, so the peaks are more peaky over here, the troughs are more troughy. Here, everything is a little bit more averaged out. Or if you want to, zoom in on one point, right over here in cold dark matter, this guy has been really efficient at really gobbling up a lot of the material around him, whereas over here, this same guy has not been as efficient. He hasn't been able to grow to as large of a density. So based on how large-scale structure looks, we know that this is very, very ruled out. So we know that dark matter is relatively cold. The second part of this statement, which is that dark matter does not interact very much with the primordial plasma, the reason why we know that is by looking at the cosmic microwave background, the CMB, which is really just a snapshot of this primordial plasma, right? So when we look out into the universe, we're looking back in time, and eventually we get to a point where, as the universe expands, right, it's cooling. If we look back in time, it's contracting, so it's getting hotter. At some point, it's too hot for atoms to form, and so this is an optically thick plasma. And so this is opaque to light. Light is just kind of bouncing around inside of here. But if you play the movie forward and the universe starts expanding again, at some point it becomes cool enough for atoms to form, and this is relatively transparent to light, and so the light basically scatters until the point where things are cooled down, the universe recombines, and then things can stream to our eyes. And so what we're seeing in the CMB is this effectively this surface of last scattering. And we can't see what's going on inside of the plasma, but by studying what's happening on this screen, we can make some inferences. It's kind of like looking at the surface of a cloud, right? You can't see what's going on inside of the cloud, but based on the structure of the surface, you can tell what kind of cloud it is and how likely it is to rain and so on. So what we're actually looking at is competing effects going on where you have perturbations laid down for you, perhaps by a theory like inflation. And so you have these nascent gravitational potential wells where there are sort of two competing effects. You have the effects of gravity, so things want to grow and bind together due to the influence of gravity, but because it's an optically thick plasma, we have radiation pressure, which prevents clustering past a certain point. So things start to come together due to gravity. At some point, the density and the pressure becomes too high, and then things actually bounce, and it goes the other way. So there's competing effects here. Now, if I add some component of matter, say cold dark matter, that only feels gravity, so it doesn't feel this radiation pressure component, that's going to change the game, right? Because these guys, these baryons and these photons are going to be loaded down by the presence of this dark matter, right? So it's tipping the scales in the favor of gravity. So between the competing effects of gravity and radiation pressure, you're going to see a stronger impact of gravity. And that means that the compressions, the times when matter is coming together and compressing, is going to be stronger relative to the bounces, the rarefactions, which are due to the effects of radiation pressure. So indeed, when we study these maps of the cosmic microwave background and we look at the acoustic waves in the angular power spectrum, right? So we look at the odd peaks, and those are the compression peaks. And you'll see that this third peak, which is the compression peak, is relatively high compared to this second peak, which is a rarefaction peak. Now, in the absence of cold dark matter, this would actually be lower. But so the fact that it's actually equally as high means that there's some component of matter here which is loading down the baryons, which does not appear to be interacting very much with the photon-baryon fluid. Right? So it's not getting dragged out of the gravitational potential well by radiation pressure. And so this is one of the most precise ways in which we're able to say what is the matter and energy budget of our universe. And so this is why we know that dark matter outnumbers ordinary matter by a factor of 6 to 1 in mass. So that's the standard story. But now, okay, you're probably sensing a theme. I want to push on some of the assumptions and ask to what extent, or can we quantify to what extent we can violate some of these things. So the flip side is, what if dark matter could interact just a little bit with the primordial plasma, and what if dark matter was born just a little bit hot? It turns out, when thinking about this question, me and some collaborators realized that it is possible to make the amount of dark matter that we see in our universe. That's one of the actually properties that we can measure the best about dark matter. And so you can make that amount of dark matter if the dark matter interacts very, very weakly with the primordial plasma. And when I say weakly, I mean at the 10 to the minus 12 level. The way you would make the dark matter in this situation is actually from the decay of modes in the plasma. One way you can think about it is that inside of a plasma, a photon has an in-medium effective mass. And because it has a mass, it can decay to light weakly coupled particles. I want to now just make an aside about what inspired this project, which was actually thinking about stars. Okay, so inside stars, right, stars are also plasmas. And so this same process that I just mentioned, where you have these massive, effectively massive photons decaying, can also happen inside of stars. And this process can extinguish stars pretty quickly if this final state is unhindered by the plasma. So this type of process is really important to consider when thinking about the evolution of certain kinds of stars and the various populations of stars. One population you can look at and where you can see this kind of effect pretty cleanly is in white dwarfs. Okay, so I'm just going to show the white dwarf luminosity function, which is something that tells you about the cooling of white dwarfs, right? Because white dwarfs are kind of expected just to cool monotonically over time, so their temperature is telling you a little bit about their age. And so these stars start out rather hot, and they move to the right here on this diagram. And so here's some data of the white dwarf luminosity function. What this dashed line here is showing is what happens if you only have surface photon cooling. So this is essentially a Mestel cooling law, and you can see that it seems like it's a very good fit to what's happening with the data at these higher magnitudes for dimmer white dwarf stars. Right? And so this is really primarily happening at the surface, right? Because inside of the star, anything involving photons isn't going to be able to cool it, right? Because it's an optically thick plasma. And so any photons that you emit are going to basically get trapped. The mean free path is very, very short. So this seems to be a good description of what's happening up here. But down here, there's actually a considerable dip. And what accounts for that dip, and the way that you draw this blue curve here, which matches the data, is by accounting for this additional way of losing energy inside of a star, which is this plasmon process that I mentioned before. So in the standard model of particle physics, you actually have situations where plasmons, where photons inside of a plasma can decay to neutrinos. And that's what accounts for this dip here. So basically stars that would have been on this line cool down more efficiently and move faster to the right on this diagram. And that's what accounts for this shape. And then you actually see there's like a slight excess here over the cooling because you get some bunching, okay? So this is an important thing to take into account in the standard model. This has been known for many decades now. Somehow, though, it didn't percolate to people thinking about the early universe and about making dark matter. And so we were kind of looking at this situation, and we thought, it's interesting that this seems to be a more important effect for brighter and hotter stars. So in other words, hotter and hotter plasmas. Where else do we have a hot plasma? Oh yeah, the early universe. So it turns out if you think about this type of process in the early universe and making dark matter, it's actually really, really efficient at making dark matter. Actually, as far as I know, it's the most efficient way of making dark matter thermally in the early universe. So what happens here, what could happen here potentially is you could have this plasmon. If you have dark matter that has, let's say, a dark version of E and M, so it has a dark photon, the standard model photon is going to naturally mix with that dark photon at some tiny, tiny level. And so you could have a situation where it mixes and then that decays and makes the amount of dark matter that we see. And again, this would be a really exciting situation because it would be telling you something about what's happening in this dark matter sector and the existence of a new dark force, if this is the way to make dark matter. So this is something that we would like to test, right? This is a really kind of crazy sounding idea, right? Making dark matter out of light. I think that sounded pretty wild when I first thought of it. And so the way we're going to constrain it is by having an insight where it turns out that the dark matter that you make from this process of plasmon decays is as hot as possible. So here I'm putting hot actually in quotation marks because when you solve the full Boltzmann equations for the distribution function, the phase space of dark matter, it turns out it's highly non-thermal, okay? So if I look at the probability that my dark matter is moving at some speed, right, it has this kind of funny shape. Whereas here is, what you would expect from a thermal population. So it seems like you have this peak going on at low speeds, low momenta, and then you have this very fat, high velocity tail. And so what's going on here is that when you make dark matter this way out of light, it turns out that decays are preferentially happening in the rest frame of that particle because of time dilation effects. Right? That's why muons can survive as cosmic rays and can hit the Earth. Right, so the fact that things want to preferentially decay at rest is why you have a peak here at low speeds. And then you end up with this high velocity tail here because as the universe is expanding and cooling, the plasma mass is changing. Right? The plasma mass is a strong function of temperature. So over here in this high energy, high speed tail, these are dark matter particles that were born at a slightly earlier time when the plasma mass was a lot higher because the universe was hotter. And so these dark matter particles inherited kinematically a higher speed from a heavier decaying particle, effectively. So you have this fat tail of high-speed dark matter particles, which is kind of reminiscent, actually, of massive neutrinos or of warm dark matter. So I'm going to tell you now about some preliminary results where we're trying to set limits on this dark matter situation by considering the cosmology. So one way that we can do that is by looking at structure formation and saying, like, well, we've been looking for warm dark matter and for massive neutrinos for a long time in a variety of different ways. Let's try to piggyback off of those ways and constrain the possibility that dark matter gets born this way. It turns out that if you consider these kinds of systems, right, where we already have data and people have already done analyses, you can constrain up to roughly this level, up to tens of keV. For those who are maybe familiar with the warm dark matter literature, where existing constraints on warm dark matter are on the order of maybe 4 to 5 keV, we're actually able to go to a much higher mass. And the reason is that even though the name warm dark matter implies that those are the warmest initial conditions, the initial conditions that we set from plasmon decay is actually warmer than warm dark matter. So that's why we're able to go up to slightly higher masses. And the prospects in the future are that we can probably go up to on the order of hundreds of keV with planned probes. Okay, another piece of insight I want to mention as to how we're going to constrain this idea is that dark matter that gets born this way, that gets born from interacting with the plasma, is necessarily going to interact with that plasma, and it's going to drag it a little bit at some very minute level. So if you fix all the cosmological parameters, here's kind of what that effect looks like. Okay, so here, in this, again, is preliminary work. I'm showing the usual collisionless dark matter case in black, and then this is dark matter from the plasma decay process. And what you see here is that the structure of the acoustic peaks gets slightly modified because of this interplay that I told you about before between gravity and radiation pressure. So what happens here is that this first acoustic peak actually gets a slight enhancement. So this is the acoustic peak that represents the first time that things in this length scale have just kind of had an opportunity to come together just due to the finite age of the universe. And this compression peak is enhanced because things are coming together with a force that's stronger than just purely gravity, right? So things are clustering gravitationally, but they're also dragging their nearest neighbor with them along for the ride into the gravitational potential, which makes the compression a lot stronger. But then what happens is that when things bounce, when things start feeling the effects of radiation pressure, some of that dark matter also gets dragged out because it feels at some very minute level, it feels that radiation pressure, okay? So some of that dark matter gets dragged out, and so you end up not having as strong of a bounce, right? And then basically the gravitational potential well that I'm talking about in this configuration space picture, it never recovers, right? So it's lost some of the dark matter that would have been there in CDM, but it is no longer there because it was dragged out by this coupling between dark matter and the plasma. And so the subsequent peaks are always suppressed, right? So this potential never feels oscillations that are as strong as it would have in the cold dark matter case. And so this is what it looks like if you keep all of the other cosmological parameters fixed. Of course, you have to account for degeneracies, of this situation with ordinary cosmology. And so working with Cord Forkin to understand that, we think preliminarily, again, that with Planck 2018 data, we can set up, again, on a similar level of up to tens of keV with current data. And we've done some preliminary sort of Fisher forecasts for CMBS4, and we think we can do even a little bit better in the future. I want to say also this is not necessarily the end of the story, right? So here is a situation where we're constraining this dark matter theory. If we look at the mass, we're constraining it from below. We can also, in the future, try to probe this thing from above using direct detection experiments. So there's a huge program right now to try to look for lower and lower mass dark matter. In particular, we're using novel condensed matter systems. And so here's an example of one that I proposed. And so this could be a situation where we're using cosmology to constrain from the bottom end. We're using Earth-based experiments to come from the top end. And we're really able to robustly say something about this situation. and really able to complete a full cycle of the scientific method. So the upshot here for this part of the story is that dark matter can be made from decaying light. I think that sounds crazy, but it turns out that there are a lot of predictions so if that's true, then it's going to modify the cosmology in a way that is detectable. And so we can try to empirically test for that idea and really start from making a theory, making a prediction, a hypothesis, and then going and testing that in the data. So this is the scientific method at work. Okay, so just to briefly recap my talk, right? So I told you a little bit about how we can look for signs of dark matter dissipation by looking at unique morphologies in galactic structure. I told you a little bit about how inelastic dark matter scattering can affect the structure of subhalos, and if you add inelastic channels of scattering, things look qualitatively completely different from what we think of with cold dark matter. And I also told you about ways of making dark matter in the primordial plasma of the early universe. And the way that I told you about, as far as I'm aware of, is the most efficient way of doing that I know about. There's a lot more that I'm thinking about that I didn't have time to talk about today. And really, part of the reason why I have all these other things I'm thinking about is because if you take a step back and think about all the possibilities of what, for example, dark matter could be, really there's a huge space of possibilities here. So really, if you think about all of the dark matter candidates that we have that are allowed, it spans over 90 orders of magnitude in mass. Okay, so there's a huge range of diversity of different kinds of theories, which I have broadly classified in this way. But this is just one axis, right? I'm just talking about the mass here. So already at that level of just that one axis, there's 90 orders of magnitude. But there are other axes here, of course, right? There's the axis of how strongly can these particles interact, either with themselves or with baryons. There's a possibility that the dark matter is not one thing, but it could be multiple things. So really, there's a huge range of possibilities here. And so that can seem a little bit daunting, right? There's just such a diversity of theories that there's not really going to be necessarily one way in which we can test for all of them. But the idea moving forward is, can we explore a lot of this space essentially for free, in quotes, using astrophysical systems that were just laid down for us by nature? So not necessarily having to build a new experiment to cover all of this parameter space and all of this range of possibilities, right? So, Yakov Zeldovich said that the universe is like the poor man's particle accelerator. Actually, I think it's so much more than that, right? Because it's filled with systems that I think are interesting to study in their own right. And so my approach is, well, given that we want to study these systems because they're interesting in their own right, can we piggyback off of those observations and back out, some interpretation for different kinds of theories of dark matter? And this is something where we, again, don't have to necessarily build a dedicated experiment. Okay, so that's the plan, for my research program moving forward. I just want to summarize now and to give my outlook, which is that we can confidently infer from astrophysical observations that there's some new type of matter out there. And so now we're trying to understand what is it? What is the particle nature of this thing, and how does it behave? And again, it's a big universe. There's a huge range of length scales and time scales and environments where we can probe different kinds of theories. And this is a space where there's a lot of room for creativity. And I think that the time right now is really ripe to be thinking about this because we have so much astrophysical data coming in. Thanks so much for your attention.
Thank you very much, Katelin. Do you have any additional questions? Yuri?
You say again, what is the temperature and the density you need to produce dark matter particles from light?
Yeah, so I don't have a plot of this, unfortunately, but in the early universe, right, where you go to temperatures above an MeV, right, so these are temperatures that are hotter than the electron's mass, right? In that situation, you can make dark matter really efficiently.
At which densities?
At what densities? I would have to just plug in the numbers, but yeah, so it's just it's like a, right, so just take the temperature of the universe, it's got zero chemical potential, and so from that you can solve for the density. So it's like, yeah, it's like T cubed.
How does it compare to cores of massive stars?
I think it's probably less dense, yeah. But I would have to check.
So could you make it inside massive stars?
Yes, you could, yes. And so there actually are constraints on light weakly coupled particles because given that we see the stars that we see, if you had too many light particles that were coupled to the interior of stars, yeah, you would then extinguish the star and we just wouldn't see them. Yeah, so there are limits like that. Yeah.
So in the spirit of bounding things, you said you had your model of chord galaxies. It got more chord with self-interacting dark matter. Can you put a limit on that, given what we know about baryonic processes that also flatten dark matter profiles?
Yeah, so right, so we know that baryonic processes can flatten them, like in simulation. The question of whether or not nature solves the problem of flattening them in this way, I think is still an outstanding question, right? I think there's maybe not a huge consensus as to whether that's how nature solves this problem. At least I think that's my understanding anyway. But yeah, given that we know baryons can do this, right, there could be some interplay between dark matter interactions and baryons. And it's not clear to me that they're going to stack, right, that the sign is always going to be stacking in a constructive way. There could be some competing effects, and I'm not exactly sure. But yeah, that's why it would be great as a next step in simulations to add baryons and see if that changes the story, because everything I was showing you was dark matter only.
I just had a quick follow-up on Yuri's question, because I was sort of thinking the same thing. Can you produce the relic abundance without being ruled out by the constraints from production in massive stars?
Yes, you can. Yeah, so if I go back, to this parameter space, the constraint from stars actually kind of goes up here, goes up to here. So the cosmology constraints are actually stronger.
But this is the two-parameter space, right? There's also a coupling constant.
Yeah, but once you establish the mass, and if you require that you get the right amount of dark matter, that pins down what the coupling constant is. So it's a one-parameter model in that case.
Any final questions?
I was just wondering if you could come back to the Oort limit, to the vertical motion of stars as limits on the disk density.
Yeah.
I mean, this is a very old subject in astrophysics, right? How to constrain the disk. I was looking for the connection in your talk between what you've done and what generations of dynamicists have done before. Can you explain a little bit how it's different?
I would say the biggest thing that's different is just that we had Gaia, right? So we had a lot better astrometry. We had much more populations of stars that we could look at. So people had previously done, so Holmberg and Flynn actually established this type of analysis 20, 25 years ago or something like that. But their analysis was limited to Hipparcos data. So they were looking primarily at A stars. We're able to basically look at more populations of stars and look higher above the galactic plane than they were.
So where are the stars that you're using for this constraint?
Where are they?
Yeah.
Yeah, I mean, I can show again the plot. Yeah, so really we were looking roughly 200 parsecs, above and below the plane. So that's where the stars are, and this is how they're spatially distributed.
And this is around in our neighborhood, 200
Yeah,
parsecs?
so we looked at a cylinder of radius 150 parsecs. Actually, we did a bunch of different checks, so that volume that we chose was not random. We wanted to make sure that we were choosing a volume that was big enough so that we were maximizing our statistics, but not too big where we were violating some of the assumptions that the radial motion was decoupling from the z motion, right? If we start looking at a bigger and bigger cylinder centered around the Earth, like a bigger radius, right? There's going to be some changes along that radius in the disk, right? Even in the baryonic disk, of course. So yeah, we also wanted to make sure that we were mitigating any astrometric uncertainties, which gets worse as you go further and further away. So yeah, we looked at different data cuts in our supplemental materials, and we tried to find one where we were having as good of statistics as possible and actually finding convergence as we were making the box size smaller and smaller, but not introducing any systematics. So yeah, if you care to learn about that, you can check out our supplemental materials. That volume choice was not random.
Okay, let's thank Katelin again.